So since one of the things that we're interested in this class really is how do we actually model motion, we actually need some of the mathematical tools for modeling motion. And one of the key tools that we're going to want to use is vectors in order to describe motion. So in this clip, we're going to talk about a couple of things. First question is, what is a vector? And what are the different definitions of a vector? And the second thing we'll talk about briefly is how do we represent a vector, and there are a number of different ways of doing that. So if we talk about what is a vector, well, you can answer that question from a couple of perspectives. One perspective to answer it from is, of course, from the MATLAB perspective, right? So you've dealt with MATLAB last semester, and from a MATLAB perspective, all a vector is a list of numbers. So you might have a vector that has 2 elements, 1 and 2, or you might have a vector that had 10 elements, 1, 2, 3, up to 10, right? It's just some list of numbers. It's a one-dimensional matrix in MATLAB. If you ask a mathematician what a vector is, they'll tell you something a little bit different. Mathematician, I think that's who knows how to spell mathematician. They'll define vectors in terms of what their transformation properties are. So from a mathematical perspective, a vector is some kind of mathematical object that obeys certain transformation rules. And we won't get into that in this class, but certainly when you talk about vectors in linearity, for example, that sort of mathematical definition of a vector is one that you'll deal with some there. From a sort of physical perspective, which is of course the perspective we'll be taking mostly in this class, a vector is simply an object that has both a direction and a magnitude. So it's again a mathematical object with both direction and magnitude. And that stands in contrast with some of the other things that we've dealt with. So for example, previously we've often used scalars, which are just single numbers. Scalars have magnitude and they have a sign, but they don't have a direction associated with them. So for example, 50 miles would be an example of a scalar. West would be an example of a direction, and 50 miles west is something that has both a magnitude and a direction, so you could say 50 miles west is a vector. Okay. Obviously there are a lot of different potential units that you can have for vectors. Vectors end up showing up a lot in the physical world, so when you talk about position, that tends to be a vector quantity. Velocity tends to be a vector quantity. Acceleration is a vector quantity. When you do electromagnetism, electric field, magnetic field are both vector quantities. There's a quantity called the vector potential in electromagnetism, which is also a vector, and so on. So certainly vectors are fairly important when you talk about modeling physical systems. Well, if a vector is something that has both a direction and a magnitude, the other question we should deal with is how do you actually represent a vector? And of course, one of the common ways to represent vectors that you've seen before is the idea that you represent a vector using an arrow. So this is sort of a graphical representation of a vector. So if I wanted to talk about the vector A, right, I could draw the vector A, and the length of the vector would be the magnitude of A, and the direction it was pointing in would be the direction of A, which I would denote each of those things with A with absolute value around it. That's the magnitude of the vector A. And A with a hat over it is a unit vector in the direction of A. It's the direction of A. Now, using graphical representations for vectors is handy in a lot of cases. It allows you to very quickly get a qualitative picture of what's going on, but often to do operations on vectors, you'd like to have a more sort of formal way of representing vectors. And so a second way that you'll commonly talk about vectors is in terms of what the different components of the vector are. Now, in order to talk about components of the vector, you need to be operating in some coordinate system. So for now, we'll just talk about a Cartesian coordinate system. So I think about a two-dimensional Cartesian coordinate system. There's the x direction and the y direction. I use the notation I hat to denote a unit vector in the x direction. So all that means is a vector of length 1 that's pointing in the direction of x, of increasing x. So I can write that like that, I hat. And then j hat is a unit vector in the direction of j. And so I could equivalently write a vector, let's say my vector A looks like this. And if I measure it out, maybe it goes over 3 in the x direction and up 3 in the y direction. So I could say A is equal to 3 comma 3, or I could equivalently say A is equal to 3 times I hat plus 3 times j hat, which means 3 units in the I direction, in the x direction, or in the I hat direction, and 3 units in the y or j hat direction. And now I will move this so you can actually see what I just wrote.